in science and activism to be in the front role of people learning and just furthering their intelligence. That picture is actually really interesting. As a joke, we were having a party at my college, and the police officers came to shut it down. But they were actually incredibly nice and humble and very nice people and took pictures with us. And it was just a funny event. But my
So,
question, go
but
ahead.
so is that a police officer pretending to handcuff somebody?
Yes, it is not actually anything happening that's wrong. It's honestly a joke, a parody on somewhat on today's society.
Okay, all right.
But
Go in peace.
but yes,
Uh,
as a question, what do you think about what SpaceX is doing with the current just the way that they're doing the internet service through the satellite system and how they're giving internet service to very remote areas. Just how does that technology work?
how does it work?
Yeah.
Oh, okay. I was afraid you were going to ask me something more political, which would be difficult for me to answer. The How does it work? Well, to what extent do you not understand it? Let's go with what don't you understand about it, and then I'll tell you what I do. I happen to have a bachelor's in electrical engineering from 1965, so I'm well versed in all of this stuff. But actually, I'm interested in it, so I happen to have paid quite a bit of attention. So I am actually capable of somewhat answering your question to the extent that it isn't too highly technical. Go ahead. Ask me.
I
What's
guess
what's the part you don't understand?
yeah, the part that I'm kind of having a hard time understanding is just the ratio of satellites that are going up versus the area that's usable for people to get access to these internet just areas. So like pretty much like I understand the concept of like the mapping and using like a network of these satellites, but how has that network not been like more completed? Like is that I don't know, I guess.
Well, it's a good question, and I have to say that I'm going to err in the realm of speculation here because some of it, pretty much everything that you've just asked, I don't know the answer to, but I certainly do have thoughts about it. For example, why do we need 40,000 satellites? Why can't we just do with 4,000 like they have up there right now? That would be a question. What's the difference between 4,000 and 40,000? Right? That would be part of your question, right?
Absolutely, and that just also seems like a an angle question as well. Like how much of an angle can that radar reach and that signal reach?
Right. So I think the uh, the answer is, as you suggested, the angle. So that if there's 4,000 satellites up there, they're more widely separated from one another. So they each of them cover a wider area, and and then think about the number of ground stations versus the number of satellites. If there's very few ground stations, then a limited number of satellites should be able to cover it, except for the perhaps factor involved with the further you get from the ground station, the weaker the signal. Aside from that, which could in fact be exactly part of the problem, but ignoring that, it could be simply a matter of how many ground stations you need to cover in a single pass over a certain area. And that can be entirely about bandwidth, if you will. If you're ignoring power, it can be entirely about bandwidth. How much bandwidth can you give each individual receiver? And it's interesting to me, especially, that they are not in the business and never have been, and never even considered being in the business of trying to direct physically the antenna that they are beaming the information back. They used what's called a phased array of transmitters that can direct the beam in any direction they care to without physically moving the satellite's antenna. You know that, right?
Well, yes, of course. And another thing that comes into mind when you bring that up is, does latitude and longitude play a role in this at all? Like the further you get north and south towards the poles, does that uh, angle become harder to receive, or do the wavelengths change due to like the change in electromagnetic environment around?
Uh-huh. Well, that's interesting. Actually, the physically wherever they go, there are different weather patterns. The signal has to travel through different kinds of electromagnetic environments. So the signal might, in fact, be modified at any given time to deal with what the weather is between X and Y, between up and down. That and that weather could vary between latitudes. So yeah, but I don't think you were referring to latitude with respect to weather, though I think it's certainly, I think it's local weather, whatever that is, wherever it happens to be, they have to deal with that. Uh, and and as far as longitude is concerned, the longitude is certainly not one of the issues because the Earth rotates underneath the satellite. The satellite's path in the sky remains unchanged. Uh, there's no force on it to change its the plane of the ellipse that it's describing, but the Earth is rotating underneath it. So constantly, every hour and a half, every uh, passage around the Earth in 1.5 hours, the Earth has moved 1.5 hours away from wherever it was before. So longitude keeps changing. And latitude changes, of course, continuously as it moves around its orbit in an hour and a half. So latitude and longitude changing constantly. The only thing that is a constant is the highest latitude and the lowest latitude. Those don't change over time. Uh, and so when you launch the satellite, you make that's the choice that you make more than anything else, as well as the separation in, if you will, longitude between every satellite. I don't know still where I'm going with that because I still don't know if I've addressed your question. And I certainly, as I've said before, am not sure of all my answers here. But go on, ask.
Well, that kind of just is like it's like a continuing thought process that I've been thinking about, and just like it's not very clear at the moment. So I appreciate the thought you've given it. I'll give the time and space to somebody else.
Okay,
Thank
let me just say that I think uh, there's another process that I think is interesting and not within my realm of complete understanding, but think about this. One satellite is passing over a certain territory. Let's say there's 100 ground stations there. Okay, the satellite has only a certain amount of bandwidth that it can at any given instant use. And that bandwidth is being directed towards individual ground stations, which means that other ground stations are not getting a signal at any given moment. So what the satellite is doing is literally time sharing between all the ground stations on the ground, and therefore giving them each a little bit of its power. And the more ground stations you have, the more satellites you have up there. Also, Marcel, are you aware of the new generation of satellites that use lasers to communicate with each other? Are you aware of that?
not of the intricacies of the systems that at work, but of the concept themselves. Yes.
Because what they have to do in order to make it work. Let's say you want to talk to somebody and you're in New York City and you want to talk to somebody in Africa. How does that signal get from A to B, New York to Africa? That signal, you don't, certainly they can use to some degree ground stations to transmit the signal through transatlantic wires. But ideally, what they want to do is to transmit the signal between themselves, satellite to satellite to satellite. And to do that, they have uh, uh, created a new system of satellites that will communicate with each and every satellite to send the signal between various satellites to get it to its final destination, having bounced off more than one or more than two satellites using laser, not radio waves, to send the signal. Were you aware of that?
Well, that's a change in wavelength. It seems
What,
like an
yeah,
increase in
but
efficiency.
certainly from optical to radio is a giant change in wavelength.
Well, yeah, and it also seems like with the ground station question, it's all about a question of efficiency as well. Because if the ground stations become more efficient, then you need the less satellites as well. So it seems like both parts. It's a two-sided edge.
I don't know that the ground stations will become more efficient. They may become more efficient in the sense of that less is required to do more, but I think it's more about the satellites becoming more efficient. They can change the satellites more easily than they can change the ground stations to some extent. They're putting in new satellites with newer technology, whereas they're continuing to put in ground stations that essentially are designed to do the same thing all over the place. You know, you need 1 million ground stations. They have to be more or less the same in how they're designed, but the satellites up there can be continuously improved to do the same thing. But anyway, thank you for your question, and appreciate it. And given that I'm in small steps and giant leaps, where I'm really hitching a ride on the interest of people in this house whose real interest is in space and astronomy being, in space. We're talking about sort of the same subject, but it's really very different. It's what technology is and what technology can accomplish in near Earth orbit and near planetary orbits. But it's all technology. The actual astronomy, if you will, is all about what the universe is made of and how does it work, and and pretty much has nothing to do with technology. So, if you will, and my expertise is at least the one that I was trained with, is what the universe is made of rather than how satellites are made. But nevertheless, I'm totally interested in both. So thank you for your answer, your question, Marcel. And let's see if Arvin has a question. And remember, you folks in the audience, that's your job, is to come up here and do this, because without this, the room doesn't work, right? It's titled Ask. All right. So Arvin.
Hey, hello. Can you hear
Ah,
me?
hello. I hear you.
Yeah. Okay. Okay, because last time I was not audible and yeah, I missed my turn. But anyway, yeah, it's good to be here again. It's been a while. So yeah, basically I was just going through some news yesterday and I saw that like uh in Berkeley they're making a telescope to study the gravitational wave background. So I
Uh-huh.
just saw the news yesterday and I got very excited about it.
Right, right. Now, I just sort of read about it recently, and the idea of the gravitational wave background is
Hmm.
they've actually not just th- they've also already been able to perceive it. I believe
Yep, yep.
they've already heard the hum, if you will,
Yeah.
and
So I think this was with the pulsar timing array. I think they
exactly.
published the paper in July, start of July, I
Yes,
think.
yes. That's very true. That's very true. And to me, very exciting. The idea that they can use something that nobody ever saw coming, as
Hmm.
a way to measure gravitational waves. And gravitational waves are interesting, especially since they can literally look back before into the Big Bang. You can actually conceivably see beyond the horizon that's represented by the cosmic microwave background radiation, which essentially begins at 400,000 years after the Big Bang. Gravitational waves can be seen hopefully earlier than that as well, and contain perhaps some information that will let us know more about the Big Bang to begin with. So Arvind, would you like to try to explain it, or shall I try to explain what they have actually discovered? Because it's pretty interesting. And I only read one article on it, so I'm sort of just a little bit dim on it as to how it works. But I have a few facts that I can throw into the mix.
Yeah,
But
I
do you
mean,
want to try?
go ahead, please. No, please
Okay.
go ahead.
Okay. Well, but remember, well, let me I'm checking your profile. You have a PhD in physics at University
No,
of
no, no.
Zurich. Do
I'm
you
doing
have?
my PhD in physics.
Oh, you okay? So you should change
I
you should
just
change it.
started 2 weeks ago.
Oh, okay. But nevertheless, how old are you?
28.
Right, and I'm 78. So there you go, 50 years. So there's a good chance that you would know more than me, just by picking up your head when you wake up in the morning. But nevertheless, I'll tell you what I know. The so pulsars, really a terrific thing that they discovered in my lifetime, and it was a pretty cool thing when they discovered it. And the thing they discovered that they didn't see coming was that the pulsars, which turned out to be rotating neutron stars, were had an incredibly accurate pulse period that didn't change from minute to minute, day to day, and year to year, but does in fact change from year to year for some pulsars. So it's not like pulsars do not change the rate at which they pulse, but certain pulsars, ones that are young and have only been recently created, ones that pulse not at many times a second, but many thousands of times per second, rotating at millisecond pulses. Those are quite accurate in their pulses, and they do not change from year to year. So they can be used as cosmic clocks. And we've all heard about how general relativity has a habit of being in how not gravity, how light has been tends to be affected by massive objects such as galaxies and the like. So a pulsar that has spent uh, quite a number of millions of years on its way towards Earth will have passed various objects along its way, and 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 as a result, the the timing of, and this is where I'm a little bit fuzzy. As a result, I don't know how they do it, but but the but the accuracy of the pulses and the fact that the pulses can change as a result of the passage of gravitational waves allows astronomers to see what the pulses have been influenced by gravitational waves and frequencies that our own receivers on our planet cannot begin to do, because our receivers are only a few kilometers in length. But in order to be able to receive pulses from things that are much larger than simply the two neutron stars colliding, and you want to get two ultramassive black holes found at the center of galaxies, and you want to see them colliding, our instruments on the Earth can't begin to do that, but something that is light years in length can perceive those gravitational waves and can respond. And these pulsars are the perfect object to be able to observe that. And I believe they have 63 such candidates that they have been using for over a period of time, maybe 10 years, where they've been recording those pulses every day and all the time, and have been able to see certain background events more as a hum, but a real hum, than individual events. That's about all I know about it. Can you say any more about it, Arvin?
No, that just sounds about right. I mean, for me, I just tell myself in a very simple way that, well, I mean, the pulsars basically have a set frequency, and the gravitational wave alters the frequency, and that's how you detect it. I mean, that's pretty much how it makes sense to me. But yeah, I didn't
Right.
go through the paper, so I can't
No, I
speak
certainly didn't
in
go
much
through the paper.
detail. Yeah, yeah,
So you're going to be a PhD. You're going to have a PhD in physics,
yeah, yeah.
and and uh, and 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 that's pretty exciting. And you're just on your first year. So how many years do you think it'll take you?
It's a 4-year PhD program because I have teaching duties as well, so it's 4 years.
4 years. That's good. I always think the average number of years is seven.
Oh my
I
God.
took seven. I took 7 years, which is, and it could have been done in much less time if I knew what I was doing. But I've heard that the average number of years for PhDs in physics is 7 years. So good luck
7,
with
huh?
that. 4 years. That's terrific.
I
Nice.
mean, yeah, probably. Probably I'll take longer because I mean, I'm shifting my topic as well. So let's see.
What you wrote in your uh, uh, profile, you're searching for neutrinoless double beta decay. Is that what you're
Yeah.
changing it from or to?
Two, this will be my PhD thesis, basically. Yeah.
And is there such a thing as neutrinoless double beta decay, whatever that is?
It's theoretical. Well, we've been searching for it for over 2 decades. So
And,
now
and you want to
there's
do this, and you want to do this for your PhD to search for something that hasn't been found for 2 decades, and you want to spend the next 4 years of your life doing that.
yes, because we're really, really close.
Okay. And they're close to
Yeah.
finding such a thing?
I mean, it's that's a very difficult question to answer because like there are a lot of factors that go into the detection of such a decay. So the idea of this is that like if you have a double beta decay without neutrinos, it's basically a process uh, that violates the standard model.
So,
Because
so are you saying that you're looking for something that violates the standard model?
yes,
Oh, well, in that case, Arvin, it's certainly worth a shot because if you find such a thing, then you're well on your way to a Nobel Prize in physics.
well, it won't be. It. I mean, I'm just part of
And
a
it won't be just
collaboration,
you.
so
It won't be just you. It'll
yeah,
be a thousand
exactly.
other people as well.
250, yeah, not so big, but yes, yeah.
And where do you fall on that team? At the very tail end of that spectrum of 250 people?
Hopefully not, because like we are in charge of the calibration system, so we're like kind of in the forefront of it at the moment. So that's nice. So we get to
Wow.
play with the calibration data as well as the actual physics data as well. So it's
And
pretty cool.
is you're using data from from CERN?
No, it's at LNGS in Italy, Gran
Oh,
Sasso Laboratories. Yeah.
so it's a small laboratory that's producing the data?
I mean, I don't know if I'd call it
Well, it's not
small
as big
because
as the one between Switzerland and
oh,
France.
absolutely not. No, no, no. I mean, the entire experiment is inside a cryostat, which is a few tens of meters wide in diameter. So it's not so big.
Wow. Okay.
Yeah.
Nice. Arvin, if you hang around, Carla and I, who's next to speak, Carl and I always have a differing opinion on truth here. I always say that I have a truth, and she says she has one, and we all don't necessarily agree. But if you can weigh in on whatever Carl and I argue about, and if you happen to know anything about what she and I might argue about, then that'd be helpful.
Well, I will try my best. I will stay for a bit before I have to go. So yeah, I will be here for a bit. Yeah.
Okay, so Carla, you're up. You want to argue?
No, actually, I just came to hang out. I just came to hang out. Um,
Well, one of the let me put it this way. Okay, you believe that 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 the that because gravity is lesser at higher altitudes, that has anything to do with climate at all, except, but I agree that it has to do with clouds forming higher up, but not because there's less gravity up there, but just because gravity has a direction, meaning pointing down if you or up. So things float upwards, you know, and so clouds float upwards. I think that that's the only effect of gravity. You think that gravity has an effect beyond that, because gravity is less higher up, which is certainly true, but I don't think it has any effect beyond the fact that it gives a direction for things to float upwards. Am I correctly stating what you and I differ about?
not not really.
Okay,
Um,
tell me what we differ about.
yeah. So, okay. So if you kind of think of it like when you're fishing, you have a lure and you're like, "Here, fish, like come and get the lure." But really, once you get to the lure, I'm going to have you in my clutches and I'm going to I'm going to jerk and make sure that the hook gets stuck on the fish. I don't know if you fish
Okay.
much. Um,
I
so in
used
any
to when I
case,
was a kid. When I was a kid in the Atlantic Ocean.
yeah.
Yes, I did. Go ahead.
Yeah.
Go ahead.
So basically what I'm seeing from so I put up my diagram. So this is orographic rainfall. And so what I'm seeing is that on the leeward side of the mountain you have the most gravity at that corner. Um and then at the top you have least gravity, okay? So if we think of it in terms of the land is floating on the magma, it's just all floating just with the
Abs-
isostatic pressure.
Absolutely
Um,
true. Absolutely true.
I think
And
there are movements in the land that we aren't perceiving because we just don't perceive the movement of the land. It's like it's just not part of our perception. Um, so so basically, when the how do I describe this? Basically, all of the water flows in to the landmass. This is what I'm getting. Um, into the landmass and into the underwater, the underground water reservoir, and it's kind of led by that maximum of gravity at that specific location. And then once it gets there, it's like a bow and arrow, where it's like, wait a minute, oh, we were kidding about this maximum of gravity. Actually, up here, we have this really low gravity at the top. So instead, what we're going to do is push it all the way through. So it's like one thread going all the way through. I don't know if I'm even explaining this
well,
well.
a little bit, a little bit. But if I changed your word gravity and added one word to it and said gravity gradient,
Yeah,
okay?
absolutely.
In other words, gravity is not just a thing that's here, more here and less there. It's also a change as you go up.
Yes.
And that's certainly true.
Yeah.
So there is a gravity gradient, and so there certainly is less gravity up high and more gravity down low. And 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 you are perhaps saying in what you're saying that the gravity gradient produces the effect that you are saying it produces. Would
Yes,
that be
it's gravity
consistent with
gradient.
what you're saying?
Yeah, and
Right?
that's why deforestation has such an impact, because it's changing that gradient. And that's why also the same at just at the same token, it would be urban sprawl, you know, would also have an impact on that gradient. So once you mess up how that's supposed to fundamentally work, it becomes more difficult because the the action of trees pumping water is a passive action, so it's dependent upon environmental factors, and those are part of the environmental factors. So
Okay.
that's where
So,
I'm
so
at.
Arvin, do you have any intuitive sense of what she's talking about? And can you comment on it? Because my thing is, my feeling is that she's assigning properties to to things that are actually mediated by other things, such as capillary action, and I think that
No.
and things that are that that water in a particular area, while certainly contributing to the gravity in that area, does not have any influence at all whether there's more or less water in an area, except for the fact that the other forces that water is kin to, such as capillary action, would in fact have the effect that she's talking about, rather than somehow or other some thing to do with a gravity gradient per se. Can you speak to anything that she or I am talking about?
No, I mean, I was not able to follow it, to be fair.
Okay.
So
All right, that's fair. All right, so Carl and I have talked about this a few times, and without, I was trying to engage in, if you will, a more, put somebody else on here so they could say something, because I've said my piece with respect to Carla. But
Sure.
perhaps,
Thank you.
but perhaps we can get Shlomo, whose mind seems to be very complicated, uh, to talk to us tonight.
Good evening, Dr. Whitehouse. Um,
Good evening.
so
That is my
my,
actual name.
I know it is. Yeah,
Yeah,
I
I'm
I
just telling
probably
everybody
asked
else.
you. I probably asked you questions many months ago, but I've been listening to you the last year or two. So it's a complicated question with two scenarios. Number one, we have 13.8 billion years that we're aware of. We
Hmm.
have 2 or 3 trillion galaxies. Is that correct? Galaxies,
Yes, the
right?
number that I've
Okay.
recently seen is 2 trillion. Yes,
Yep. So we're not counting the fact that there are more stars than all the grains of sand on the planet. Okay,
right.
that's obvious. But given those factors, two different scenarios. One, assuming that there is nothing faster to travel than the speed of light, and that there are no such things as wormholes. Just assuming that
I
that
think we can
that that
safely
that
assume both of those things.
okay. Then, what is the algorithm or your perception of during a brief history of 10,000 years of civilization, or even the the human race being on this planet, or if we give the future of a 1,000 years into the future, that any other intelligence would have the ability to visit Earth. I say not one in 1,000. And a further question is, how many intelligent uh, would there be out there now, whatever now means, at the same moment in time, and how
Mhm.
many would there have been in 10 or 11 billion years since planets were formed?
Well, Carl Sagan, when he was alive, was asked this sort of question all the time, and and uh, and he he tried very uh, uh, clearly to not put his opinion too much in the front of the answers to the question. He would circumvent the question in such a way that in the end he informed you of the issues involved without answering the question himself. And I will, if I can, endeavor to do the same thing. But I will raise certain. But you've actually asked me my opinion, right? You actually did say, Laird, what do you think, right?
Well, it could only be your opinion, or opinions also that you've heard from other knowledgeable people.
Right. No. No. Absolutely. But so recently, I've seen a a few things that I actually haven't YouTube videos, which I actually haven't watched carefully enough to know exactly what they're saying, but I understand to some extent what they are saying, and I like one I've seen recently which the question ultimately comes down to something called the Fermi paradox, which I'm sure you're intimately aware of, right?
Yes, I've heard of it.
Right. And the Fermi paradox, as it's been labeled, was what Enrico Fermi was discussing with a group of renowned physicists, I think perhaps after the war. And his question was, where is everybody, as it's been paraphrased? And everybody in the room understood what that meant, which is where are all the aliens? Have they been here? Why aren't they here? Are they coming? Could they come? Where is everybody? And so essentially, that's your question. Same as Enrico Fermi's, and not voiced quite as succinctly. So the question is so here's some information, which I'm sure, and not that you don't know this, of course, but it's yeah, but the very fact that I'm telling it to you means I'm giving you my opinion. So this planet, ours, has been around for 4.5 billion years. Actually, we have even more data than that, 4.56 billion years. And life on this planet has been around for 4 billion years, give or take a few hundred million years. And, and it took all that time for life to evolve to a point where it can produce us. And us being, if you will, organisms with backbones was only produced in the last 500 million years, or 1/9 the history of our planet. And since then, it took quite a while for us to get here on this planet to be discussing this issue. And so we've only been here for a very short amount of time. During all of that time, somehow or other, life has never been wiped out on this planet. And that's pretty neat and nice for us. And if it wasn't so, we wouldn't be here to discuss it. So there's no way that I can give you statistics on that. On the other hand, I am about to give you just that. Uh, the idea that we have survived the asteroids that are constantly passing by our planet is quite amazing. The asteroid that wiped out the dinosaurs and wiped out 90% of all living things, and I may be misquoting, on this planet was the result of an object that I believe was in the neighborhood of 10 kilometers wide. There are lots of objects passing by this planet that are bigger than 10 kilometers wide, and they don't hit us. And the reason they don't hit us is because all the ones that were bigger than 10 kilometers wide have already hit the Earth. And we have suffered those encounters long ago in geologic history. So their marks on this planet have disappeared. So billions of years of impacts by large asteroids didn't manage to do anything to destroy life on Earth because it had taken hold, and as long as there was something left, it continued to evolve. Maybe it was interrupted for quite some time while some very advanced organisms died out. But we managed to get here somewhat unscathed through all of those impacts, all the supernovas that came our way, all the electromagnetic transmissions or ejections from the sun, all the comets. We got here safely. And the question is, how many other civilizations could have done the same? And by my very bringing the topic up, I'm implying that I think that other civilizations equally moving forward through evolution as we did might have suffered much more than we did and maybe never made it to the stage that we make it. And we, at this stage in our lives, are certainly looking up at the skies and saying, you know what? A nice big asteroid could come by and wipe out wipe out life on this earth, so it could take another 100 million years for it to resurrect itself to the point where it can, in fact, begin this discussion all over again. So, how many planets have suffered our fate, that have suffered the fate that we did not suffer, is the question to which nobody knows the answer. But I propose it as being an answer to your question as, where are they? Maybe they just have been knocked out before they could get here. That's one of many of the answers to the question of where are they. And you can look it up, as I had in the past, not recently, but you can look up the 100 answers to the question of where are they and come up with 100 different scenarios as to why they're not here. So which one would you like next?
Well, the next further question is, the parameter I set up was not being able to travel faster than the speed of light. So that restricts us, obviously, to not being able to escape this galaxy for at least 100,000 years at close to the speed of light. Never mind the other trillions of galaxies. Second question is, comment.
Let me just stop you right there. Okay, in the conversation that we all have about life and aliens and all that stuff, it is never proposed that any civilization could have come here from a different galaxy. That's off the table, completely off the table because of the speed of light. So we don't, and wormholes. So that's off the table entirely. So it's only our galaxy that we're talking about. Continue.
So you've already explained natural phenomena and the likelihood of what could happen in a moment or not, and also at some time in recent history, I think 2,000 years ago or whatever, the human race was down into the thousands or hundreds of thousands. We almost did perish. That's just my comment. Is that correct?
As far as I know, you're absolutely correct. And as far as people say that, it's a theory. It's not proven per se, but it's certainly been put out there many times.
Now, my next question, that if you care to respond, I'm sure you will, is not one of science. It's Michio Kaku. And I
Uh-huh.
know you're familiar with him, and he
Uh-huh.
says that we are at level 0, and if
Okay.
we don't get to level 1 by the end of the century, that's the end of the human race.
Uh-huh. Okay. And you want my opinion about what he said?
Yes.
Well, although I don't like him particularly, I agree. I agree. I wouldn't put it in such stark terms because I wouldn't begin to think that I was as well informed about the future of our future as he is. But on the other hand, I see no reason to argue the point. I think that we are fairly doomed. But if you ask the question, human race, okay, I think the human race has a longer history than the next 100 years. But I think the human race, as we know it, which is that everybody's glued to their cell phones, may easily disappear within 100 years if we don't get it together. And so, yeah, the human race, as we know it, yeah, could disappear, and perhaps permanently, because, for example, let's say that we wipe ourselves out with atomic weapons, and we are left with very few living humans on this planet. Let's assume that humans can survive an atomic war instead of just cockroaches. Otherwise it's just the cockroaches, and they'll take 100 million years to get here, to get to the level that we are. But if humans survive, then the question is, what will they have to work with? Because one of the things that what we have done is we've depleted our natural resources, and 100 years from now they won't have the technology to use those resources. So I really think that if we do destroy ourselves, but still are human at the end of that time, we may never rebuild our civilization to the level that we have it now. And so we will cease to be a communicating civilization. And so as far as the rest of the universe is concerned, we have disappeared. So we will have only appeared in the universe as a detectable civilization for perhaps a couple of 100 years, and then we're gone, even if we survive for millions of years thereafter.
You did not. You mentioning natural resources. We didn't touch yet on hydrogen. The use of hydrogen as a source of energy is barely at the beginning, and it's the most abundant element in the universe. So,
But
and one
how do you use hydrogen, Shlomo? How do you use hydrogen? You need energy to separate hydrogen from oxygen. In order to do that, you have to have a way for sunlight to dissociate hydrogen from oxygen. And to do that, you need electricity. And to create electricity, you need a civilization.
Well, I'll answer that. I'm a bit older than you. I'm 81 years old, and in popular science or popular mechanics, 50 years ago, a man was shown with his uh, Airstream Winnebago and his Cadillac, and he had a garden hose filling up both vehicles, and I assume that they but if they were, I can't, for the likes of me, I can't understand how powerful the oil industry could be to uh, to to prevent, like they did with Tesla, his tower, etc., from becoming the norm. But assuming he was correct, he was running the vehicle with some kind of conversion system and separating the H2 from the zero, from the oxygen, and the vehicle was running, and out of the exhaust pipe came
Wa-
H2O once
water.
again.
right.
Yeah.
But
So was that
but
a? Do you recall that
well,
vehicle, that van?
I've been, I used to subscribe to Popular Science, not Popular Mechanics. I didn't like Popular Mechanics as much. I didn't see the vehicle, but I, being almost as old as you, certainly was interested in that stuff. But the question, Shlomo, is do you think that there is a technology that exists today, known to perhaps only a few people, that could be used to separate hydrogen from oxygen in such a way that it didn't require energy from the sun in the form of photovoltaic energy. Is there a way to separate hydrogen from oxygen and use that as fuel without inputting energy? Do you know of such a mechanism?
No, and I doubt there is one. So I
So
question
do
why
I.
that man was featured at that time,
Because
40, 50
be-
years ago.
because bullshit existed then as well as now. That's all. It's as simple as
I
that.
understand.
Bullshit.
Will
Yeah.
will the biggest invention since the wheel be the battery that is the size of today's car battery that will have thousands of times the capacity to power a jet airplane or whatever. In
Uh
other
huh.
words, a concentrated
Uh huh.
the new battery.
Yes.
Will that be the most important invention that mankind can make in the future?
Well, yes, I would say yes. And you and I have lived so long, and we've watched batteries go from lead acid to a nickel metal hydride to lithium batteries. And during that time, the concentration of energy in a battery has not increased by more than, and I'm just going to make up a number here, 5 times. Uh, and and what you want to propose that we need a battery that can concentrate energy 1,000 times. And Shlomo, if such a thing was invented, it would change everything. What we could do is we could power we could reverse climate change if it was, conceivable. We could launch satellites up, power them, send the batteries down. I mean, we could do anything. But the main thing is airplanes. You could power an airplane such that it could fly without using fossil fuel. And if you could do that, that would make a big difference to to climate change, for sure. Uh, and cars could run on it, and 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 you could change the battery instead of powering it with by waiting for 20 minutes to power your battery. You just pull up, exchange a battery pack, and put it in your car and go on your way. That could be a very easy thing to do. In fact, cars have been designed to do just that, but the battery that's being exchanged is absurdly large. So yeah, that would be a great
Well,
advance for sure.
or you made me come up with two more questions. I only had one, but the one that you got me to question now is that there are two types of um, of electric vehicles. The type in America where you take the vehicle and you charge it with electricity, quick charge, slow charge at your home, wherever. The other type, which did not take off, but it was invented and in use, was in Israel. I think you know of that one, where now the reason it didn't is because it's a very small country with limited distances to travel. But that was a battery exchange where the battery up to 5 times, as you mentioned, the concentrated energy would run the vehicle for a few hundred kilometers a day, maybe, and then you would pull in a station and they would pull out your battery and put in the new battery. But I believe that
Right.
was in use 10 years ago.
I remember that my daughter, who was a reporter for a few years in Israel, about maybe 2 decades ago, or decade ago, no, a decade and a half, she told me about that vehicle in Israel. So it does ring a bell. Uh, and it was an Israeli invention. It never went anywhere. Yes, and but I don't know much about it except what you just said.
And my last question, I forgot. How do you like that? So that gives me something to speak to you about next week or
Which is what?
in the future. I can't remember the question, my final
Oh,
question.
okay, okay. Right.
Okay, thank
Well,
you so much.
but hang around because remember this room only works with people on the stage. So if you can hang around, please do. And I
Yes.
appreciate the fact that you're older than me. So if anything, what we would do if there's nobody on the stage, we would reminisce about the good old days. But let me invite Bert to speak right now, and then we'll see how that goes. And if we don't get more people, then we could go back and discuss the good old days. So anyway, Bert, hi.
Good evening, Laird. How you doing?
Good.
I'm
Nice to
glad.
hear you.
Nice to hear you. Hey, are you familiar? There's a Netflix documentary on black holes. Have you ever seen that?
I've seen so many, and I
Uh huh.
I don't know if I've seen this one, but I chances are no because I don't think there's any news about black holes that I haven't heard of recently.
Yeah. So this was produced by Peter. How do you say his last name? Gillum, and he's from Harvard, and he's from the Event Horizon team,
Oh, that's nice.
the
Okay.
ones who
Yeah, yeah,
imaged.
and that's cool. That's very cool.
Yeah.
To be on the
So
team that imaged a black hole for the first time. Sure.
yeah, yeah, this is an amazing feat. Anyways, just a heads up. There's actually a proposal out there called the Event Horizon Explorer. So, just to
Uh-huh.
give people a little background, the Event Horizon Telescope is a conglomeration of radio telescopes all around the globe, and excuse me, on any given time, they work together, all observing the same supermassive black hole, such as Sagittarius 87, or what was the other one?
M87 or Sagittarius A.
Right, right. Sagittarius A, M87. So, excuse me, got a little cough.
Gesundheit.
And
Gesundheit.
anyways, the Event Horizon Explorer aims to put a radio dish into space to extend the baseline, because the ones on Earth act like a radio dish the size of the Earth.
Uh-huh.
Now imagine one in geostationary orbit, right?
No, I can't. I don't know how you do that. No, no, really, I don't know how you do that. I'll
Right.
tell you why, because from the point of view of physics, and Arvin might be able to weigh in. And so I'm not saying it's impossible, because obviously, if they think they can do it,
Oh,
they
it's
can do
definitely
it.
possible. Yeah.
What I don't understand is how. Uh, and let me explain why I don't understand. In order for these telescopes to work, they have to know they record independently of each other the light wavelength, the light. I'm saying light, but it's
The
actually
radio
radio
signal.
waves,
Right.
right? But I'm
Right.
saying light because light is the thing. Uh, uh, the electromagnetic waves coming from the black hole, and then what they do is they record the phase of the the energy,
Right.
not just the energy itself, but the phase. And the phase is important, but you need to know the distance between the two telescopes quite accurately so that you can make sense of the phase, because a little bit of distance, a little change in distance between one telescope and another would change the meaning, what the phase means to the model that they're using to create, to absorb the data. So when something is in outer space, the it it strikes me it might be difficult to know exactly where it is because it keeps moving, whereas something on the Earth is quite stationary, and once you've got it pinned down, it doesn't go anywhere. So the satellite that's up there doing this job would be very differently configured because it keeps moving. So you'd have to include that in your algorithm. And I guess that's possible too, because they can measure where it is to within a fraction of the wavelength of visible light, and they only have to get it right to within a fraction of the wavelength of radio light. So yeah, it makes sense. Sure, why
You
not?
worked through it. Exactly.
Yeah, I worked through it. Right,
Yeah.
right.
And so that's the idea. So if you're at geostationary, then you've just multiplied the size of your telescope by 10. If
Right.
you're at L2, you've got a baseline, million and a half kilometers.
Mm-hmm.
So what they're doing is they're aiming for the very high frequency, the fine detail, what's called the photon ring, to be able to
Uh-huh.
image that. If they can do
Ah.
that, and they can do that on, say, a dozen or a couple dozen black holes, woo, that's gonna be amazing.
Uh-huh. Yeah, no, I
Anyhow,
love black holes.
so my
Yes.
PTR is actually a meeting that's going on at NASA Goddard this week. Um, Peter Guilliam is there. Peter Kaczynski from Goddard, people from Harvard, Smithsonian, a bunch of institutions gathering to work out the technology, the science case, doing a bunch of calculations to make sure everyone agrees that what is necessary. How big of a dish do we need? Things like that.
Uh-huh.
Um,
That's
so
nice.
they're actively working to put that proposal together for kind of in response to the astrophysics decadal study, which came out in 2021, which talked about extending the Event Horizon Telescope into space, and so this is kind of happening in real time.
And so those people that you have in that picture are uh, are all dedicated to the proposition, how can we extend the
Yes,
Event Horizon Telescope? That's wow. That's wild.
yes, yeah. So there's some of the best black hole scientists in the world there.
Boy, I'd like to be in that room.
Yeah,
No, really, I happen to be, I love being in the presence of movie stars, but I really love being in the presence of scientists doing science. It's scary good, and the reason that I like it is because I learn exactly how much I don't know about the subject that I'm interested in. People are often like myself, spouting about things that they know very little about. Well, one of those things that I know very little about is astronomy. I know a lot about a little, or a little about a lot. That's what I know. And those people know a lot about a little, which changes everything in terms of, because you can barely understand what they're saying, and yet you think you should be able to. But it brings you up right up, by your it gets your attention. Oh yes, right. And I
yeah.
use that sort of
Thank you.
information to remind me about what things I shouldn't have opinions about, which is pretty much everything. I try as much as possible in my life to remain humble about the things that I don't know anything about, and try not to voice an opinion, despite the fact that I have one at the ready at any given moment. So it's rooms like that that teach me how to keep my mouth shut. So I would love to be there. Anyway, so Bert, what else can we do tonight besides talk about that? Because we do have Elliot, but he just came, so we don't know if he's going to be the thing that's going to get this everybody up to the stage, or we don't know, or maybe you're the one who will get everybody talking about the next subject. So do you want to talk about black holes in some way? How about this? How about the idea that there are trillions of black holes in the universe?
Right.
Uh, yeah, I saw something recently. I forget the number exactly how they quoted it exactly, but it strikes me there was a time we didn't have black holes, and now we do. And now, not only we have black holes, but having the gravitational wave astronomy, we now are kind of very aware of the fact that black holes are everywhere, and some of them are falling into each other, and so we can see them. But the idea now that, so it really in the last decade, I think we have begun to appreciate that the universe may have a ridiculous amount of black holes. I'm loath to say compared to the number of stars, but I wouldn't be surprised if somebody told me that the number of black holes was equal to the number of stars. I wouldn't necessarily argue that they were wrong. I don't know the proportion of black holes to stars, but the very idea that the fabric of space is, is dotted with holes in the space-time continuum is really an interesting image, you know?
That's
It, imagine the universe has got, you see all those stars up there? And imagine if you say to yourself, for every star I can see up there, there are black holes up there, you know, just as many. I think it's probably less, but I don't really know the
probably.
proportion.
Probably.
Yeah, actually,
Um,
it's a good thing to know.
right,
A
and
proportion,
part of also some of the scientists study active galactic nuclei. Some study primordial black holes. Um, so yeah, there's quite an active research on that the questions that you were just asking.
right? And also the question comes up now: uh, which came first, the chicken or the egg? Which came first, the galaxy or the black hole?
Exactly.
Uh, and and they are still working that one out
Right. And if you
with
want a
James Webb.
Roman, and just real quick, if you want a Roman space telescope update, I took these pictures here through the observation deck into the clean room. You can see in there in my PTR on the left, those black pieces are solar panel mock-ups. They're not the actual ones. The actual ones are in California being populated with solar cells.
Oh,
But those are the ones they're using to put onto the outer barrel assembly mock-up to be able to like do some vibration tests and to like just do fitting tests and things like that. And then on the
wow.
right, that
Uh-huh.
silver hexagon that the people are standing around, that is the spacecraft bus for the Roman Space Telescope. And into that, they are affixing different panels with avionics and communications, electronics, things like that.
I don't see the people.
Let's see, are there people in there? Yeah, yeah. The if you look closely, there's people in white suits, so they're hard to see, I guess.
So are they much smaller than the than that hexagon ring?
Yeah, that hexagon thing is probably about, I guess I would say 10, 11, 12 feet across.
Uh-huh. Still don't see people. So why don't you tell us what the Nancy Grace Roman telescope is going to do? That's pretty exciting.
Right, so that is going to give to us a better view. Okay, so I zoomed in. By the way, you're right. There's no people in that picture. I apologize.
Uh,
I'll put up a different one that does have some people, but the Nancy Grace Roman telescope is a Hubble class instrument, Hubble class telescope observatory that instead of having more multiple instruments that take a little field of view and image or do spectroscopy or such like that, it has one instrument called the wide field instrument and one called the coronagraph instrument. And the coronagraph instrument does take a very tiny field of view, like an arc second, enlarge it quite a bit, looking at another star, and do some very fancy wavefront shaping and coronography, Leo stops, masking, and such to bring out the contrast while blocking the light from the host star and to be able to see light of the orbiting planets or exosystem of dust and such like that.
how far is the coronagraph arm extended from away from the telescope to essentially block out the star?
No, it happens internal on the optics bench.
So
It's
it's
just
really so it's really
no,
close
yeah,
to
there's no
the
extension or
focal.
anything. They actually
Oh,
form internal images along the optical path where they block some light and let other light through. And they have these complicated looking masks. They have these Leo stops. They have wavefront sensing, shaping, and all of that works together to eliminate the light from the host star. And
and this
and
this is your field, is it not?
so yeah, I'm an optical systems designer.
Right. So this is like your meat and potatoes, and this is really cool.
It is. It is.
Wow.
Um, but then the wide field instrument is where I was more involved with the design, and that's going to have a 300 megapixel field of view. And the field of view is like if you took the Hubble instruments together, is still like 50 times more than that. And it has a element wheel with 8 bandpass filters, 2 dispersive assemblies, and it does full field imaging about the size of the full moon every
So,
photo.
so how long will it take to do a sweep of the entire sky? How long does
Well,
it take to do a sweep of?
it won't do a sweep of the entire sky.
That's right, because
But
something's missing.
to give you an idea, Hubble did a 22-day survey of the Andromeda Galaxy, where it imaged about half of the Andromeda Galaxy with about 400 something images
Hmm.
um, over a couple years of observing. Um, Roman Space Telescope would be able to repeat that survey in a few hours
How is that possible?
because it uses a dedicated wide field instrument at the prime focus of the telescope, and the telescope is a 3-mirror anastigmat optical design, which means it has a primary, secondary, and a tertiary mirror working together to form a flat field image. And so you can put a large focal plane array of 18 sensors, each with 4K by 4K sensors, pixels. You get about 300 megapixels over a quarter of a square degree field of view. Again, about the same size as the moon. And
And is this a result of the increased fineness of the technology, so that essentially you can squeeze more pixels into the same area that the Hubble would have had less pixels?
so the sensors on the wide field instrument are what are called Hawaii H4RGs, 10 micron pixels. They're the same sensors in James Webb Near Spec.
Uh-huh. Uh-huh. But
Uh,
how do they compare to the Hubbles? Because they
so
also have near infrared.
Hubble Advanced Camera for Surveys and the last Wide Field Camera 3 had H2RGs, which were 2K by 2K versions of these sensors made by Teledyne.
And these are not 2K by 2K, but what?
4K by 4K, and there's
So
18 of them in one focal plane.
do I multiply 4 by 18 to get a number?
Multiply 4.088 squared
Uh-huh.
times 18.
And that's but it doesn't seem to work out that I beat Hubble at its game so quickly. It's got some other toys in there that make it even better, right?
Well, the fact that it's not in low Earth orbit, um, Hubble has like a 60% downtime,
Ah,
right? Or maybe 40%. Yeah, maybe 40% downtime, 60%
right.
uptime. This is out at L2, just
Uh-huh.
like James Webb, so it can operate continuously. There's no slewing and settling type thing issues with the thermal conditions changing every time it's going in and out of shadow, things like that. And mainly it is uh, it's more efficient. The
Uh,
sensors are better, so you get a little bit more quantum efficiency, I would say. The F number is faster. It
mm,
is an call it an F8 prime
mm-hmm,
focus.
mm-hmm.
A lot of the Hubble instruments are like F24.
Oh, uh-huh.
Um, so the exposures you can do. several 300-second, which are like 5-minute exposures. You move around a little bit so that you kind of like pixelate the image, depixelate the image, if that makes sense.
Mhm.
Fill in the gaps between the sensors, things like that. And the Roman Space Telescope, if you remember, was originally called W-FIRST, the Wide Field Infrared Survey Telescope.
Right.
And so it's going to take a picture, and it'll do a bunch of little dithering things, like I said, to fill in the gaps. Then it'll move one step over, do the same thing again, move one step over, do the same thing again. It'll do like a row of them, and then it'll drop down and do another adjacent row, drop down to another adjacent row. It's going to cover about 5% of the night sky um, over its lifetime.
Oh,
Um,
only 5%? I'm sorry.
only five, right,
No,
right,
I thought
and
that,
and
I thought it was much bigger than that,
yeah,
like 60%.
yeah. No, so I think it's about 5%. Remember that there's a lot of solid angle, I guess, and there's areas that are of higher interest than others. Certainly, there's a lot of overlap with the Rubin Observatory
Right. So,
surveys,
so what is the
as
Nancy
well as
Grace Roman?
Euclid.
What is it? What is its primary mission? What is its
Dark
point?
energy, yeah, dark
Dark
energy,
energy.
cosmology, time evolution of the universe.
Ah,
What is the mass and energy distribution of the universe? How did it change over time? So really
nice.
looking for clues to dark energy and dark matter, um, that because you can't see it directly, you look for evidence of how it affected things as they changed.
And with the increased data that it has, how will it do that better than what we have now? What
Hmm.
data points will it add that we don't have right now? We have
Yeah,
some. It's going
it's
to
all
add
about
more.
statistics, right?
It's going to give us better statistics.
Yes,
We have
right.
some now. We're going to get some later. What the statistics are? What the statistics
You're
on what?
looking at galaxies, looking at how they shift both in spectrum as well as position, as well as what you would call stretching of the point spread function, meaning if the image of a very distant galaxy passes near a gravity source off to one side, it can
Uh-huh.
kind of actually get elongated a little bit. So there's a science team that is specifically going to be measuring all of these elongations, and that
Elongations of
of the images of these very distant galaxies, and based on how far away those galaxies are, and where did those stretchings occur. In essence, you're mapping out where was the mass, the gravity, the energy, as the over the time periods of the universe. Fascinating.
that's fascinating. Also interesting enough that I don't understand it, but that's interesting. No, no, that's where
Right,
I
right,
begin to start to have to know something about this stuff that I hadn't even considered before. I did know that it was, in fact, designed to deal with dark matter and dark energy. I did know that,
right, right.
but I
And it's also
really
in
didn't
doing
know how.
such big surveys, it's going to find a lot of things, right? I mean, people are going to be mining this data like crazy for years, even after it's taken. Um, and it's going to find supernovas going off all the time, and other observatories with dedicated spectral analysis can, such as James Webb, for example, or ground-based telescopes, could quickly go and say, "Hey, let's take measurements of the supernova." So,
Now, Bert, I want to ask you a question that I have asked all my friends who are technical, and not a single one of them has ever answered it correctly. And so I am going to ask you this question, and I assume that you will know the answer off the top of your head, as well as what I mean by the question. Here's the question: how many star radians are there in a sphere?
That's
oh, sorry, I
sort
was
of my
muted. I was
Oh,
muted. I immediately
okay.
said 4 pi.
That is the answer. That is correct. You win the prize. Nobody in the history of my life has ever answered that question. The so here's the funny thing, boys and girls. Everybody that you know of you've ever worked with, ever studied with, talks about angles. But nobody that you ever worked with, who studied with, except maybe those people who may have taken solid geometry in high school, like I did, would ever use the word star radians. You know that you can measure angles in radians or in degrees or radians. Some of you may know that. But when it comes to angles that are measured in terms of a portion of the sky, you can no longer talk about an angle. You have to talk about a portion of the sky. You know that a sphere is the surface of a sphere is 4 pi r squared. If r is 1, then the entire surface of a sphere is 4 pi. So therefore, portions of the sphere are portions of 4 pi. I asked Bert, what's the entire sphere? He told in terms of star radians, which is the word you use when you can no longer say angle. You say star radians. And he said correctly, the answer is 4 pi. Nobody that I have ever met can ever say that. I love you, Bert. And let me ask you one
Ah, I
more thing.
love you too, Laird.
And when you, I'm sitting in the front seat of a car, and I'm looking out the window, and I'm thinking to myself, boy, look at all those star radians that I can see versus the people in the back seat. And I ask the people in the back seat, uh, or at least if I'm traveling with a group of people and we are tourists, and some want to be in the front and back, and I can never say to them, I have more star radians in the front than in the back seat. And nobody ever seems to, I could never say that. I could say a better visibility. But what I really mean to say is the angle of the sky that my eye subtends in star radians is much larger when I'm sitting in the front seat than the back seat. And I can't say that, but you understand, Bert, don't you?
Yeah, we took had to take a radiometry class, so
Yeah, yeah. Okay,
I'm
so
familiar with it. And I actually just used it in a calculation a couple of weeks ago.
that's great. I love this stuff. Okay, can you hang around? I want to
I,
make sure that Haris
can I,
and Elliot and Buddy,
can,
and yes, Shlomo.
yeah, my question to Bert, and I won't be able to phrase it properly, but the star ratings, or when a telescope looks at what appeared in the past to be empty space, even billions of light years out, and in the past, and now it's revealed that there's a lot in that empty space. So if we take the circumference of with us at the center, will a single telescope or an array of telescopes, what percentage of the volume has been mapped?
You mean
There's
the area? Do you mean volume
the
or
area,
area?
the area of the total universe that we are able to visibly search to the edge of the universe. How much has been mapped now? 2% of everything?
About 2%, maybe more, maybe 10%. And Nancy Grace Roman is going to do a better job uh, than that. Uh, but in fact, we're blocked by the Milky Way, so very little of it. We can see portions of it that are not blocked by the Milky Way, but we spend the money looking away from the Milky Way. It's not 2%. I'm sorry. It's more like 80, 90%. What's the number? Do you think? What do you think, Bert?
I mean, it depends. What wavelength are you talking, and what
Wait,
are you talking about? Just we have pictures of the whole sky, certainly, but do we have
invisible light.
detailed?
Invisible light.
Yeah, do we have detailed survey studies of everything? It depends on
What
how you
percent of the
define.
sky has been mapped, at least to some level, uh, by the surveys that have been done, like
Well,
the two
100%.
mass survey? What?
I mean, 100% has. But like
Uh,
you said, you can't see past the galactic core.
right.
So,
And
you
you-
know,
and the disk of the Milky Way blocks uh, everything except the infrared.
right,
So
right.
optically, we can't see there.
Yeah, that's a good question.
Right. It is a
All
good
right.
question.
Well, I'll go now, and I'll just listen in. And
Thank you. So I
thanks.
think the next person is Haris, if I'm not mistaken. But I did see Elliot come up before you. Reese. So it seemed to me as Elliot was next, but in terms of
Yes, Elliot was above. Yes.
okay, even though PTR order, Elliot is after you.
Hello.
Hi, Elliot.
Oh, it's been very engaging, this whole thing, and I'm not even sure if my question is, relevant or technical, but I've this, I am disconnected from the math and the fit of physics and everything. Like maybe I can look at a sheet of music and I can see the notes, but I don't know, I can't feel the music, but if we all listen to the music, we can hear it and understand it.
Hmm?
And so I was kind of curious about like how the math relates to the physical world. Like, do we see squares and cubes? Like, you say like E equals MC squared. Like, how do we see like squares represented in reality? And how do we see, the math? I mean,
Uh,
is our math representative of what we see, or do somehow like squares and things exist in reality that we can
you're talking about
observe?
what you're talking about something as simple as fundamental geometric shapes, which, if you will, is mathematical and can be described mathematically, but we can also describe it to the naked eye so that we don't need math at all. So that's one of the things that, in fact, are accessible to non-mathematical people, whereas uh, uh, E equals MC squared is not. That has to be explained. So I'm not sure what your question really is, but you're coming from a musical background, right?
Not necessarily, but like, do we see squares represented in reality, or is that just one of our mathematical constructs we use to
Oh, I see.
explain reality?
Oh, in the physical world, uh, squares exist to the extent that biology or physics has is organized according to that. I don't know of any natural thing that is in fact square. Perhaps the crystals of salt are in fact square, or salt or other natural phenomenon do form natural repeating geometric shapes,
Okay, but we don't see
which
naturally occurring square roots and squares and cubes in larger
well,
astronaut.
again, from the point of view of crystals, but if you will, pentagons, probably not. Pentagons exist on a dry earth, on a dry desert sand. The shapes that are formed in dry sand after a rainfall tend to have five sides. And and hexagons are a really neat way of stacking produce in a supermarket to take the least amount of space and yet to be to have as round a shape, which is useful. So there's, but seven-sided figures, I don't know, eight-sided figures. So, I don't know. There is some reality in nature to those many-sided figures. Triangles, for sure. Equilateral triangles, probably not as much. But again, I'm not sure what you're really asking.
I guess the larger question is, I don't know, as a mathematical layman in that way, it's like I see a lot of square roots and squares and physical equations about the universe, perhaps, but maybe those are just perhaps trying to balance equations and not necessarily trying to.
Well,
We don't see those types of
well,
reoccurring exponential figures in reality in the same way.
math has taken us beyond what we can display uh, physically. For example, the when we try to solve quadratic equations, quadratic equations can be represented by geometric shapes and can be solved by moving little cubes around so as to solve the equation and determine the roots of the equation. Uh, and 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 that was done for many years uh, at the beginning of mathematics. But uh, through the Middle Ages and beyond, there were quadratic equations whose answers were the square root of minus one, and that could not be represented by geometric shapes. So in those days, they simply said the equations have no solution. For example, the equation x squared equals minus 1. What is the solution of x squared minus 1? How can you build two sides of an object such that the product of those two sides is minus 1? You can't, right? Unless, of course, the sides happen to be imaginary. And imaginary is something we invented in recent millennia, not millennia, but in the last 100 or 200 years, I'm not sure, I'm not a historian, to explain the result, the answer, which is square root of minus 1, which doesn't exist physically, but does exist mathematically. And without the square root of minus 1, it would be fairly impossible to describe something known to you as quantum mechanics. It has been proven that without access to the square root of minus 1 as a concept, it is impossible to describe quantum mechanics without that concept. And yet, quantum mechanics describes the real world, but requires an imaginary thing in its equations in order to describe it. And I think that accesses, in some sense, your question.
Yeah, it definitely does. It's certainly something to think about.
It's actually been only proved in the last few years that minus one is square root of minus one is necessary for quantum mechanics to be able to be fully formed. It's only recently that somebody actually proved that.
My question with quantum mechanics is like when you say like are two particles in the same place at the same time, or is that only theoretical or like a guess?
Well, it's never quite said that way, you know. It's it's that's never really an
Right. Yeah. Yeah.
yeah. It's what is that the real discussion of quantum mechanics simply says that there's a probability that things can be here or there, and but I don't believe that there is in fact a given maybe there is a finite probability that two things can be in the same place at the same time.
I don't
I
think I
guess
meant
I
to
guess that's
suggest that. Just that, you know, what is it? That it's either here or there, and there's no place in between, or I guess it.
yeah. I mean
That
that's
something can be in two places at the same time. They claim that. I believe they claim that, right? That a
well.
particle can be in two places at the same time, something like that.
That's the way you can reduce it to absurdity. Uh, what it sounds like when it sounds uh, equally crazy, but not quite as
Sounds
absurd.
like an average.
The idea is there's something called the double slit experiment. Have you heard that? You know what I'm talking
Yeah.
about? Do you know what I mean?
Yes.
Okay, so double slit experiment, you send electrons through two slits, and the when you e- have one slit or the other slit open, the electrons pile up behind one slit or the other. When you open both slits, they don't open up and pile up behind one slit or the other. They pile up in sort of a wave formation that shows that the electron has passed through both slits at the same time as a probability wave and interferes with itself as the probability wave. And so, if you will, passes through two things at the same time, although the object itself it cannot be split. So you could say it's in two places at the same time. But that's when you are referring to it as a particle. But when you refer to it as a wave, which is the wave particle duality thing, so when you're not looking, the electron becomes a wave and passes through both slits at the same time. And why would you be upset about that? It's a wave, and waves can do anything they want, passing through two slits at the same time. It's just when you
Yeah.
demand that they be material and be simply a particle that it becomes absurd.
Is the particle passing through a wave-like substrate?
No, it's passing through a hole, literally a hole, or a slit, if you will. And it's nothing sophisticated. It's simply a line drawn through a piece of steel or a substance that lets the electrons pass through.
But we can distinguish between the particle and energy generated through a wave.
Well, I wouldn't say energy generated from wave. We can
Uh,
say we can distinguish between the effect the electron has on itself as it passes in a wave-like manner through both things at the same time, and interferes with itself in a wave-like manner, just like ripples on an ocean interfere with each other to produce
so a
crests and waves.
photon interferes with itself.
Photons interfere with themselves, and you don't have any problem
That's
with that
weird.
because you think of it as a wave. But as soon as you think of photon as a particle and you wonder how it interferes with itself, then you got to go back to the wave particle duality.
Duality.
Duality, both at the
Like the
same time.
crest of a wave? Or
No,
where
duality
do we
means
see that?
it means depending upon what you decide to measure is what you see. If you look for particles, you'll see particles. If you look to see for waves, you'll see waves, and you can't see them at the same time. You have to choose, and the electron knows what your motivation is, and it decides to be one or the other, and to trick you. And if you assign consciousness to electron, you'll get a lot further in your understanding of this than if you try to imagine that nature does this all by itself. Uh, and if you
Do
are
we have to
assigning consciousness,
choose?
because the electron chooses how it should behave based upon how you measure it.
I
That is really cool. I did not know that.
Yeah, and and furthermore, uh, when they perform experiments designed to trick the electron by saying, "Okay, electron, we're not going to try to determine whether you're a particle or a wave till after you've gone through the slit, and then we're going to check to see whether you're a particle or wave." The electron knows that you have the intent of going to do that and changes what it is based upon what you've done after it's passed through the slit. And that is called, I think, the delayed measurement thing,
what are we
experiment.
assuming about the electron here?
I'm not assuming anything. I'm just portraying it as conscious. I'm not assuming anything. I'm
You're
saying is
portraying
that's
it as conscious.
right. Now, I do not pretend for a split second to actually think that that's true. I'm just saying is quantum mechanics is quantum mechanics is sufficiently absurd that any explanation you give is no less absurd than any other. I've just chosen to give one that is patently absurd.
Okay.
You know, so because otherwise you really have to go with the idea that nature is in fact somehow or other indeterminate until we look. If you That's called the Copenhagen interpretation, and if you assume that nature requires an observer in order for reality to exist, you get into equally stupid areas very
Right,
quickly.
but you don't believe that.
I'm sorry, it's not a matter of belief. It's an explanation that is easily refuted by logic, but on the other hand, there is no explanation for what is observed that is acceptable to any single group of people on this planet.
We love to
There,
believe a lot of things.
yeah, but quantum mechanics. See, this also brings up what you were saying earlier. Uh, there is the mathematics is real, but when you try to turn the mathematics into something physical to explain, let me show you. I have a model here. here's an electron, here's a proton, here's a slit, here's a screen. When you try to do those sorts of things and turn it into real stuff, you can't explain it by things that we accept as being reality. You have to go with the math because what your conception of reality doesn't work to explain what's seen. So you have to go with the math, which does, but then as soon as you want to change it back into something that you can accept as being reality, it fails. Such as the nature isn't real till you look. You like that? Not really. Nobody else does either, but there you go.
I mean,
So,
we see the mathematics fail sometimes.
oh, the
Like,
mathematics and quantum mechanics is one of the most prized
well, in
fields of
yeah, in
physics.
quantum, but I was thinking of string theory, for instance.
Oh, I don't know anything, but string theory
I don't
doesn't
really
have
know
any.
that much either, but it looked like they were trying to go further than they could with our current, conception of mathematics.
Yeah, they don't have. They have math, which is beautiful. They like it, and they don't have any experiments that have been able to be proposed that have been able to prove the existence of any of the truths that the string theory likes to claim as being possible. So it's simply something that awaits scientific evidence. Whereas quantum mechanics is just the opposite. It has all the evidence it needs.
Oh yeah, no, they do fantastic.
Right, right.
I guess they even have the computers now. I don't know how they're doing. I mean, that was big news a few years ago. I don't know how quantum computing is doing recently.
It's everybody likes it. It's
Okay.
it's got its admirers, and it may in fact change the way we do everything. But right now, it's not doing that yet. It's not being used to break codes, and it's not being used to encode things more cleverly than they have been encoded before. But hopefully, when we eventually break codes with quantum computers, we'll be able to build codes that quantum computers can't break. Hopefully, we'll win that race. But anyway, whatever.
Indeed.
Indeed, Haris, did you have something you wanted to talk to us tonight about? If you're there,
Uh,
Maybe-
yeah, if you have a minute still.
no, no, I have a minute. In fact, I've got at least 16 minutes, if not more. But
Uh,
16 minutes is the scheduled end for the room. But anyway,
okay, I appreciate that. Something we talked about last week piqued my thought for a question this week, and often your rooms do that for me. Uh, like when we think of radio, like well, when I think of radio, I think of like what we produce here on Earth with our technology. But like once in a while, like you get here I get read the news about bursts of radio coming from a galaxy a billion light years away.
right?
I guess one, is that the same radio, and two, what
Yeah,
would generate that?
and to what?
What would generate that in a galaxy far, far away?
There was a recent article about a burst of energy from a galaxy far, far away, and that made headlines, and it's nothing special, but it did get some play, and I'm trying to remember what the answer was. It's nothing. It's nothing. It's nothing magical. It's nothing interesting, really. I forget what the actual explanation, what the observed phenomenon was, and I forget the explanation that was given to explain it, both. But that was a couple of weeks ago. Let me see.
There was one that you're right. Like, and that, and it did. I remember that article, and it said burst of energy. But I do remember like articles of years past were described as burst of radio. Like I remember that word being used on occasion, and I just made me wonder, like, is it the same radio that we use, that we
Yeah.
can generate, and like what would naturally create radio?
Oh, everything.
Oh, really?
Yeah, yeah.
Oh,
Everything creates radio. It's just that much of it is very low frequency, very low frequency, but and in low intensity. But so,
oh.
for example, if you have an event that takes place in X-ray energies, the it that event, which may have a peak in X-ray energies, may have uh, uh, a, a spectrum that decreases in energy as you go down the spectrum, but it's still available to be observed in radio waves. Uh, so,
That's
so
really
for
interesting. I always thought they're mutually that they're different things. Please
no,
go on.
that they observe different things. They observe different things for sure, but they aren't necessarily caused by different things. For example,
Uh,
a no. If a star explodes, okay,
yeah.
and you get lots of visible light and X-rays and neutrinos and all sorts of stuff, but the area outside the star has been excited by those X-rays, and the the molecules that have been excited by the X-rays are raised uh, to high energies, and when they drop back into lower energies, they can generate parts of the electromagnetic spectrum that is no longer in visible light, but is in radio light. So carbon monoxide, or hydrogen hydrogen oxide, which is HO, and other much more complicated molecules will generate radio waves when they are excited, and they are part of the gas. They're not part of the explosion, but they're part of the gas that has been subjected to the energy of the explosion. So they can be observed independently of the light, and they occur somewhat simultaneously with the actual energetic phenomenon that you're talking about. But they're produced by very different atomic phenomena.
Wow, I've never heard the term radio light before.
I don't think I said the word radio light, but
Oh,
radio. Uh, I don't think I said that word. Uh,
okay. But you see, electromagnetic, I think, is the term used. Okay.
yeah, right. Uh, so
Oh, that's really interesting.
yes, the star forming regions in the universe are also radio bright, and different phenomenon. I mean, different phenomena produce that energy. Uh, for example, if you have if there is a magnetic field in a galaxy, and all galaxies have magnetic fields, uh, such as our own. When electrons rotate around magnetic fields, why do they rotate? Because the job of magnetic fields is to constrain electrons so they move in arcs around the magnetic field. Well, when an electron moves in an arc around the magnetic field, that electron is accelerating by the fact that it's very nature of the fact that it's not moving in a straight line. So that electron then produces a radio wave, right? So
Hmm.
radio waves are being produced everywhere in the galaxy by everything that moves, because everything in a galaxy is charged except for the neutral atoms, and neutral atoms don't respond to this thing that I just said, and they have an entirely other phenomena that explains why they produce radio waves, and nothing to do with magnetic fields. So it's all very complicated physics. But you get the spectrum everywhere you look in the electromagnetic spectrum. You find uh, energy being produced in that part of the spectrum for various reasons, all of which are generally different from one another, but may have a single source in common. But the actual mechanism is different.
Wow, thank you. I've wondered that for years, and I can't. That was the greatest, simplest, simplified explanation I've ever heard. Thank you. That really great.
Remember quasars, quasi-stellar radio objects. They are they were they were discovered, I think, as radio sources before they were discovered as optical sources.
Oh, really?
I think
Oh.
that's right. I'm a little bit. Oh, so we have a physicist in the room, Sadiq. Sadiq, is this true? Sadiq, do you
Hi,
know this to be true?
hi, Laird. Thank you so much for accepting my request. Thank you so much. I was listening to you guys. It was a wonderful conversation, and I really appreciate the effort that you're taking to come here and to talk with the audience. Uh,
So,
well,
so,
uh, yeah.
were quasars first discovered as radio objects?
I'm not sure, though my knowledge in astronomy is bit, only with the foundation which I'm working with right now. I'm a material scientist. I do simulations.
Okay.
Well, hello.
Yeah, I'm here.
Yeah, I did my master's in physics here in India. Then I went to Spain to pursue my master's in nanoscience. I was doing my
Nanoscience.
research. Yeah,
Nanoscience. Oh, that's
nanoscience.
cool.
Yeah.
That's cool.
Then I was doing my research there. Then my father expected I had to come back to India. Then I started a small foundation where we actually connect with people those who are interested in this. So where we are actually working on astronomy, like we have different astronomy projects, like we communicate with the public. We make some sort of workshops in basics of astronomy and even astro photography workshops. And right now we are into radio astronomy also. We do data driven astronomy courses. So unfortunately, I'm not able to answer your questions because
Okay.
some
I was just
resource
hoping,
person.
because I forget more than I remember. So I was hoping but I think it's true what I said. Radio first, uh, then it was determined that the object was a point source in the sky, and then a redshift was assigned to that object, and that's when it became known that the object was in fact uh, uh, at ridiculous distances and therefore extremely energetic. Uh, but I think it was first found in the radio, and I have to check, but
Yeah, could be,
yeah.
sir. And one more thing I would like to, like, if you are interested, like, we have a platform. So where we actually connect. I'm from Kerala. I don't know whether you know about Kerala. It's down south of India.
My wife calls it Corella, uh, and
Wow.
and no, I haven't been there, but she has been on board the boats in the rivers in Corella in the winter.
Wow, lovely. So now you know the place, and yeah, we have like we connect with universities and schools. So what I was thinking, I was just going through your profile, sir. You have so many videos in the YouTube, and you take a great effort, and for connecting with people. And more than that, the first line I was reading, like Carl Sagan was my doctoral thesis advisor.
Yes,
So
yes.
for many Keralites, is like not only for Keralites, I guess for the entire world. So maybe I was thinking if you could do some brief video, since we are a non-profit organization, if you can make 1 or 2 minutes video for us, we will upload it in our website so that people can I mean, they can look for your videos in the YouTube, and maybe
Well,
one day, I don't know, maybe we can have an interactive session, or
oh,
in the
I'm
clubhouse.
very much, as you can see here, I'm very much interested in an interactive session, but because of it has a certain energy. But in terms of me lecturing, you've seen my videos on YouTube,
Yes.
and those lectures are very carefully researched and prepared for, and then I get in front of a class of people who know nothing about astronomy and have very little interest for that matter as well. And they're really only interested in asking silly questions, the kind of stupid questions that I get in this room. And And so I, in fact, have learned very much that I'm more interested in answering the questions than in delivering the lecture. So I'd be very happy to do something for you if in an interactive fashion. Uh, for example, on a Zoom session, I'd be happy to do a Zoom session, and I'd be happy for you if you wanted to record it. But it's your job to bring the people, and my job to give you the answers.
Sure, sure, sure. I'll do that. So for example, what I was trying to say, for an advertisement purpose, or to just to give to the people, like just 1 minute video or something very short, so that people will get to know about your work, and we can also organize a session, as you said, an interactive to be, since you feel the energy there, the interaction. So we can bring in people, and one day definitely we can have. I mean, we can have more people through the group, and so, and the meantime they can also go through the videos which you already uploaded.
Yeah,
That way.
one of the videos I uploaded was me giving a lecture in Istanbul. But again, I was physically there,
Okay,
and
okay.
certainly if I was in India right now, I would be happy to give a lecture in front of your audience if I was physically there.
Sure, sure,
But
sure.
the last time I was in India was like 10 years ago, and I don't think I'm coming back anytime soon. So, uh, so no, it's I don't know that I could do anything for you in terms of what you're asking, but I'm certainly willing to do it if it makes sense.
Yeah, yeah,
You
yeah,
know,
yeah,
and
yeah.
making a 1 minute video about my work does not make sense because this is my work. And if you want to see it, the replays are on, and you can play those replays uh, to any audience you like. They're up there on Clubhouse for as long as Clubhouse will continue to exist, I imagine. It's not really very good as a replay. It's just good if you're here, you know.
Yes, sir, I totally agree. Maybe what I'm trying to say, maybe you didn't get. It's just you have so many content. You are doing great work. So I just want to let the people know about your work. That's all.
I
I
would
mean,
love
it's
that.
not.
I would love you. When Clubhouse first started, most of the people who came into this room were from India. And yet, since in the last year or so, uh, very few of the people are from India now. So on a given evening, maybe only one person or none who come from India. So you're the first tonight.
Okay, sir. Okay.
Yeah,
Thank you.
uh,
Okay.
yeah, but and I don't know why. I have a feeling it had something to do with the pandemic. That people stayed home in India and perhaps elsewhere in the world, and that's why Clubhouse succeeded during the pandemic. But now, with the pandemic being over, people just come when they come.
Yeah, even myself, I just opened Clubhouse like 2019. Then after like almost 2 years, I was not using this. And now I'm doing some simulation work. So I thought I have some time, and like I just started using it 1 month before, something like that. So
When you say
now people are.
what sort of simulation work are you doing?
Well, I do the adsorption studies, Monte Carlo simulations,
Uh huh.
and MD simulation. I do absorption studies of
What's MD?
sulfur.
What's MD?
MD, molecular dynamics.
Molecular dynamics.
Dynamics, yeah.
And so do you are you dealing with quantum mechanics or not?
Some cases not yet, because we take empirical data, quantum mechanics. I used to work when I was in Spain. I was with the team to do DFT, density function theory calculations. That time I used solving the Schrodinger equation, all these things. But now I'm more into simple things. My idea is to just to propagate these techniques to the young generation, like like for example, the students in BSc, or the graduate students, or PG students, or even
You,
PhD students.
you are
So we
working with
conduct.
nanotechnology, are you?
Yeah, yeah. I did my master's from nanotechnology in my nanotechnology from Spain, northern Spain, a place called Basque Country.
Uh-huh.
I
Sure.
was with the DIPC, Donestry International Physics Center. I did my master's there.
So what could you tell us about the future of nanotechnology? What should we know about what's going to happen that's going to change our lives as a result of advances in nanotechnology?
Well, that's a big question, and I don't know I'm the right person to answer for that. But
Well, you're here. You're
yeah,
here.
as far as I know, it was a very fancy thing late in early 20s, or I mean, 2000. So it was a
Yeah.
very fancy word, and a lot of money was put in this kind of research. But maybe if you um, see the real what it actually changed the human life, day-to-day life, uh, there are some application in the medical field, and
Do you
even
think that we will be able to use nanotechnology to do better diagnostics of the human body?
yes, yes, definitely, definitely, because there are so many, especially in nanophotonics and all. That's one area as a human being, because we are like human beings, and it should somehow directly affect our life, so this is one area which I find it's really worthy, for example, especially in diagnosing tumors, and the other field is like drug delivery, drug designing and all, because that became more like what to say, customized medicines, right? I mean, for
Uh-huh.
each person you design a medicine according to what he need. So where and all nanotechnology, or this drug delivery kind of thing has got wild application, and it's going to change the future. Like, soon we'll have medicines which is prescribed just for us, and somebody will design it, and we'll get that medicine.
How long
So
do you think
that
it'll be? How long do you think it'll be before we have something that will be useful to deal with cancer, for example?
cancer, yeah, cancer, especially tumors in brain and all. No, it needs high precision, because what to say, like when we when we do the chemotherapy and all, it some way affect the other part of the brain as well, no? So for high precision, there are some techniques where you can really target the cancer tissues, or for targeting uh, the exact place, right? So hopefully within even now there are some techniques, but hopefully within next 5 or 6 years we'll have so many changes in the medical field. That's
Right.
what I look forward. Yeah, and that is one thing. And there are so many other applications, but they don't really change human life, drastically, like any other invention. So being it's a fancy topic, nanotechnology, where I find it's not, maybe people get confused when they hear about nanotechnology, it's something different, but at the end it's physics and chemistry, right?
Yeah.
So yeah, maybe if you just go behind the word of nanotechnology, that fanciness, maybe you won't see many things, but on the other way we are moving ahead, far ahead, in especially in physics and chemistry together, it's nanoscience or nanotechnology.
So I always think of nanotechnology uh, because I really don't know much about it as being little mechanical robots walking across a plane, somehow powered by sunlight or some sort of chemical energy, and that these things will eventually be miniaturized so they can be inserted in our bloodstream and perform uh, 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 intelligent surgeries in our bodies, and that sort of stuff is not real, right?
Yeah, that's about our human perception, no? When we somebody explain about nano robots, what we
Yeah,
see is we try to relate it with the normal robot, but in
right,
principle it's the same absorption, or when you go to the nano level, that 10 to the power minus 9, all what you see is molecules or atoms, maybe molecules. So it's
Yeah.
actually the interaction of molecules with other, what, for example, the study which I'm doing, it's actually zeolite. We do the study of adsorption of carbon dioxide or carbon sulfur dioxide in zeolite. There is Zedism 22, which is actually a good adsorbent, a natural absorbent. So what happily actually happens, there will be some molecules inside our body as an adsorbent, and we'll send some other things, so they'll interact, they'll find a way to interact, and to altogether they'll send some properties. Or this, for example, imagine there is a cancer tissue in our body, and through our bloodstream we are sending these molecules, and it get attracted at some point, and it is giving a fluorescent effect. Just imagine it is giving a fluorescent effect.
Uh-huh.
So if you have any, like for example, any technique to visualize where is this, exact the right precision of, where these molecules are sticked, and from outside, if we can sense it, then we can give that chemotherapy or that part with high precision, no, which will not damage the other tissues around. So this is some way, maybe when we talk about, it looks very fancy. It's as if we feel like, some humanoid are going through the bloodstream and doing all these things. But yeah, see, actually what's happening is, yeah, we can relate it, it's
Cool.
how you
Cool.
communicate with the people.
Very good, Sadiq. Thank you.
Hmm. Thank you, Sandeep.
Uh, since it's past 1 o'clock, I'm going to invite Jimmy to speak, and then 1 o'clock New York City time. And Jimmy, conceptually, you might be the last speaker. So, what do you got for us? Definitely have a nice icon there. Uh, and so we have some sort of alien on some alien planet looking up at an alien sky, wearing some alien costume, Jimmy Gumdrops. And what do you have to say for yourself tonight? I hope you do. Otherwise, I'll be ending the room soon. Jimmy, are you there? Okay, so I think this. So let me just tell you all that you should check out my YouTube videos, Laird Whitehill, and you should check out my website, which is not that exciting, but it does mention the links that I used to prepare my astronomy course years ago. So you can take a tour of the universe through my links. And uh, what else would you might do? You might find 9 not particularly valuable YouTube, TikTok videos that I don't mention there. And that's it. You should just come back next week, Tuesday. I expect to be here doing this, what I do now, uh, every week till the foreseeable future. Shlomo, you appreciate the fact that as I get older, I can do this less and less, uh, but I appreciate you being here. And so we'll just end tonight. And I'll be waiting your return at a week, Tuesday, 11 o'clock, every Tuesday at 11 o'clock. And next time I'll be in astronomy and astrophysics because I alternate between those 2 rooms. So